Now this will relate V1 to V2, but our aim is to develop relationship between V2 and H. So for that we have to somehow change the value of V1. So it means that if we can find out the pressure head at 1 and pressure head at 2, how can we relate this pressure to this pressure? Pressure at this point, what is the pressure at this point? Is equal to atmospheric pressure. So at this point pressure is atmospheric. So we apply the Bernoulli principle. So P atmospheric divided by rho g plus velocity head. What is the velocity of this layer? If this area is considered very large and since head remains constant, then velocity is 0. This layer is not moving in this direction with any velocity, 0 plus z1. So what is the height with reference to 1? With reference to 1 is equal to h minus z1. So h minus z1 is equal to what is the pressure at this point? Is equal to P1 divided by rho g plus z1 plus V1 square divided by 2g. So with the help of this relationship, which is developed with the help of Bernoulli equation applied at these 2 points, at free surface and 1, we can relate this pressure and velocity to this pressure and h. So with the help of this equation, we can write P atmospheric divided by rho g plus h minus z1 plus 0 plus z1 is equal to this thing, P atmospheric divided by rho g plus V2 square divided by 2g, right. So z1 is cancelled, P atmospheric is cancelled. We will get this relationship V2 is equal to root of 2gh. Now this is developed by considering a ideal flow. Now if there is an ideal fluid flow, then there is no energy loss, because in this Bernoulli equation we have not considered any loss. And we know that whenever we have a real fluid flowing through some pipe or anywhere, if it is flowing, then there is some loss, right. So to take care of that loss, we have to incorporate some constant which is known as coefficient of velocity. So this is designated as CV. So V2 actual, this is the actual velocity, this is the theoretical velocity at Wiener contractor. So V2 actual is equal to CV root of 2gh. So now we can find out the actual velocity of the jet at Wiener contractor with the help of h. We can measure h in our lab. We have conducted this experiment, you might have conducted this experiment. This h is constant here and we can measure and we can find out CV, right. Once we know the CV, then we can use this formula and we can find out the actual velocity. Now if we want to know what is the discharge, then discharge is equal to area multiplied by velocity. So what is area at the Wiener contractor? Area at the Wiener contractor, let us say it is AC. AC multiplied by actual velocity is CV root of 2gh, right. Okay. Now we don't know what is the area at Wiener contractor. So what is the relationship between area at Wiener contractor and area of orifice? Suppose this is the orifice area, which is equal to A naught, is equal to pi by 4 d square naturally. But at Wiener contractor, because of the inertial effects, this area at Wiener contractor is little less than the orifice, right. And this area at Wiener contractor and area at the orifice is related with coefficient of contraction Cc. So Cc is equal to area at Wiener contractor divided by area at orifice or area of orifice, right. So by invoking this relationship, in which we have to find out the Cc, then we can write Q is equal to discharge is equal to Cc multiplied by AO. This will give you area at vena contracta. So, area at vena contracta is equal to Cc into AO into actual velocity. Actual velocity is Cv multiplied by root 2 GH. Now, if we write Cc into Cv, where Cc is known as coefficient of contraction, Cv is known as coefficient of velocity, and Cc and Cv multiplication is designated as Cd, where Cd is known as coefficient of discharge, then Q actual, this is actual Q is equal to Cd A naught root of 2 GH, where A naught is the area of orifice and H is the head available in a tank. So, with the help of this we can find out the discharge, or if we want to calibrate it first, then we have to calculate the Cd first. So, Cd is equal to Q divided by A naught root of 2 GH. And what is A naught root of 2 GH? This is the ideal discharge basically, A naught multiplied by root 2 GH. Root 2 GH is theoretical velocity, and this is the theoretical area at the orifice. So, A naught into root of 2 GH is ideal discharge. So, Cd is known as actual discharge divided by ideal discharge, or it is also known as a theoretical discharge. So, Cd is always less than 1 in case of orifice, as in case of the venturi meter and orifice meter also, right. So, for finding out discharge, first we need to calibrate it. So, we need to find out the Cd of an orifice, and then once we know the Cd of an orifice, we substitute here, and we know the area of opening area of orifice. If we find out H with the help of lab work, we can find out the actual discharge.